In 1934, Enrico Fermi, Emilio Segre, and associates bombarded uranium with neutrons. They subsequently observed the emission of beta particles. This indicated to them that heavier elements than uranium, actually elements with atomic number greater than that of uranium, were being formed. Otto Hahn and Fritz Strassmann in 1938 showed that this bombardment resulted in the formation of barium, a heavy nucleus, but still less massive than uranium. Lisa Meitner and Otto Frisch in 1939 found that uranium was undergoing a fission process, and smaller particles of similar size, like barium and krypton, were being formed. These particles would then decay via beta particle emission, and it is that Fermi's team observed. So what was going on in Fermi's and Segre's experiment? Well, thermal neutrons, that is, neutrons with low kinetic energies, were better at producing a nuclear fission, as the combination of their neutral charge and low energy allowed them to stay close to the nucleus for a longer period of time. When this happens, the thermal neutrons become part of the target nucleus, and the size of the nucleus grows such that some of the nucleons are outside the range of the strong nuclear force. The nucleus stretches out until it splits, or fissions. This is something called the liquid drop model. So, what was happening in Fermi's and Segre's experiments? First, they used neutrons, which, as we saw in the last section, are ideal for nuclear reactions because they are not repelled by nuclei. Second, they used thermal neutrons, that is, neutrons with low kinetic energies. These thermal neutrons don't bounce off the nuclei very quickly. They stay closer to the nucleus for a relatively long period of time. When this happens, the neutrons become part of the target nucleus, and the nucleus grows to an extent that some of the nucleons are outside the range of the strong nuclear force. In terms of the liquid drop model, the nucleus is said to stretch out until it splits apart, or fissions, and that's what we see here on the right. We have our thermal neutron entering uranium-235. We can imagine that it elongates a bit and then splits into these two smaller parts with the release of further neutrons. In nuclear fission, the target nucleus splits into two nuclei of smaller mass and a number of neutrons. The general equation for the fission of uranium-235 is as follows. Uranium-235 is struck by a thermal neutron and forms uranium-236. As you can tell by the asterisk, it means that their uranium is in an excited state. It then fissions into these two products, X and Y, some neutrons, and some energy release, which ends up being kinetic energy of the product particles. There are a number of different outcomes for this, or channels. Here are two possible examples of fission reactions for uranium-235. In both cases, we see a thermal neutron added to the uranium-235, resulting in uranium-236 in an excited state. In the first case, it breaks down into barium-141 and krypton-92 with 3 neutrons and some added kinetic energy. In the other case, it becomes xenon-140 and strontium-94 with the emission of 2 neutrons and some kinetic energy. Now, the energy release in a fission reaction is actually quite large. The smaller nuclei are stable with fewer neutrons, so many neutrons emerge from each fission. The neutrons can be used to induce fission in surrounding nuclei, and this causes a chain reaction. Enrico Fermi built the first self-sustaining nuclear reactor in Chicago in 1942. And if you want, go to PhET and look at the simulation for this reaction. Nuclear fission is used in some modern power plants. Here's a schematic of a nuclear power plant. The fission process occurs in a reactor vessel, here in the diagram shown in red. This vessel contains the radioactive material and some mechanism for controlling the fission reaction, moderating it, absorbing some of the neutrons, preventing it from getting carried away. The heat generated by the reaction heats a primary loop of water, turns it into steam, and that in turn heats another container of water, which is used to drive a steam turbine, and that turbine in turn turns a generator which provides us with electricity. The nuclear reactor is controlled by regulating how many neutrons are free to strike uranium atoms. Cadmium and boron control rods are excellent neutron absorbers, and they're used carefully, adjusted to absorb the right amount of neutrons to maintain a self-sustained but controlled reaction. You might have heard the term critical mass. This is the mass of the fissionable material that is required for a sustained nuclear fission to occur. Nuclear reactors are designed with layers upon layers of safety features, and there is no possible way for a reactor to cause a nuclear explosion. Nuclear weapons are designed to explode in a massively uncontrolled chain reaction and are very, very different from nuclear reactors. Now let's look at nuclear fusion. Hans Bethe in 1938 postulated that the reason the sun doesn't cool down, despite the massive amounts of energy it is releasing, is due to the fact that it uses nuclear fusion. Nuclear fusion is the combining of two lighter nuclei to form a larger nuclei, and that results in the release of more energy than was put into the reaction. This occurs for elements on the lower part of the binding energy per nucleon chart, where it has a large positive slope. The heavier elements formed have a greater binding energy per nucleon, which implies a decrease in mass, hence a release of energy. Here's the sequence of fusion reactions in our sun that lead to the formation of helium, along with the energy released per reaction. First of all, two protons are combined to form a hydrogen-2 nucleus with the emission of one positron and a neutrino. The release of energy is 0.42 MeV. Then a proton combines with the deuterium nucleus, or the hydrogen-2 nucleus, to form helium-3 with the emission of a gamma ray and a release of 5.49 MeV. Then finally, two of these helium-3 nuclei combine to form helium-4 and two more hydrogen nuclei, two more protons, with a final release of 12.86 MeV. The net effect of our solar fusion process is to transform 4 protons into a helium nucleus plus 2 positrons, 2 neutrinos, and 2 gamma rays. Very massive stars can create elements up to iron via the fusion process. Elements heavier than iron, as we've said before, are only created in supernova explosions as they require more energy input than is released in the fusion reaction. Nuclear fusion requires an incredible amount of energy to begin. In our sun, this energy comes from the high temperatures and pressures found in its core. These high temperatures and pressures cause a plasma to form, plasma being the fourth state of matter, where atoms are highly ionized and the electrons are separated from their nuclei. It's there in this dense plasma that the fusion reaction can take place. A nuclear fusion reactor would have great advantages over a fission reactor. Its fuel, hydrogen isotopes, deuterium and tritium, that is, hydrogen-2 and hydrogen-3, is far more plentiful than uranium-235, and it produces far less radioactive waste. So far, efforts to create sustained fusion reactions have not resulted in one that is sufficient to provide more energy than is put into the reaction. The problem is an engineering one. Physical containers would melt because of the high temperatures of the plasma. Magnetic fields are being used to control the plasma, but the energy required for the magnetic fields is greater than the energy output of the fusion reaction at this time.